All right. Can you see everything? Okay. Sounds good. All right. Thank you for coming. This workshop will focus on going over dynamic programming, which is a pretty big topic, but we'll try to get the most important parts covered. It can be kind of a scary topic for a lot of people, just since it just kind of has a reputation of being more difficult, but it actually turns out to be a pretty natural way to solve a lot of problems. So we'll first start by going over like kind of what it is in general, and then I think what will actually help get it across is going through a few examples. One classic one is generating the Fibonacci sequence. Then we'll go over a few different ways to use dynamic programming to solve that. We'll go over more generally deciding when and how to use it, and then just go through more examples, and then with the contest and also prizes. Or yeah, we'll also have prizes after this last contest. So what is DP? Generally, it's a method of taking a more difficult problem and solving it by first solving smaller problems that compose it, and then putting those answers to the smaller problems together to solve the original problem. And yeah, you can't apply this to all problems. A necessary condition is that the optimal solution of the main problem must be able to take advantage of the optimal solutions of smaller problems. And then there are some really famous examples for DP problems like Fibonacci knapsack or the Tower of Hanoi, but these are just things like, if you've heard of these are all DP. So we'll start with the Fibonacci sequence. Super quick recap. It just starts where the 0th number is 0, the first number in the sequence is 1, and all later numbers are the sum of the previous two, right? 34 is 13 plus 21. We can express this really concisely mathematically as a recurrence relation. And this is basically exactly what we just said. And then, for example, the second Fibonacci number is then the first plus the 0th. Here's an example of the third Fibonacci number, second plus the first. And then now from this mathematical relation, we can actually translate this pretty directly into code. We're saying if the index of the Fibonacci number is less than or equal to 1, really we're just caring about the cases where it's 0 or 1, you return the index itself. Otherwise, we return the previous Fibonacci number plus the Fibonacci number 2 numbers ago. Does this look good so far? Yeah. So if we look at what actually happens when we call this with an input, let's say Fibonacci 4. Fibonacci 4 will obviously be the first call in the stack. Fibonacci 4 is not less than or equal to 1. So it's going to have to make 2 more calls, first to 3 and then to 2. So first we'll look at the call to 3. That is also not in our base case, so it will call again, calling Fibonacci 2. And then same thing for 2, but then finally we'll get a base case. So Fibonacci 1 will return 1, Fibonacci 0 will return 0. This allows the call to 2 to resolve. Now 3, hello.
Is that a big deal?
No, that's the other.
Yeah. Now Fibonacci 3 has had its call to 2 resolved, so it will now call Fibonacci 1, which is again a base case, and this can finally resolve and bubble up. And then now we call 2 again. I think you get the pattern, right? So these all resolve, and you get our final answer of 3. This is what these are all the calls we made just to compute Fibonacci 4.
You know, where is the wall?
ACM Clubhouse, that is,
Across?
Yeah.
Are you doing from computer talk?
Yeah.
Oh, yeah, it's right. Yeah.
Okay. Hi.
Sorry. Just take the seat.
Okay.
This link to the side.
Yeah, I guess we can do a super quick recap.
Should I bring
Oh. You can access like the first slide.
I guess I can answer. So I have to go to this. Perfect.
Yeah. Because they don't have a projector. So we're like projecting our slides.
Okay. So this is for the Zoom link.
That's the slides link, which has the Zoom link on it. If you want to go actually direct to the Zoom, add a dash, then Zoom at the end of that link. I'm not sure. Okay. See, yeah, we'll run through this really quickly. So basically, we're exploring how we'll use dynamic programming to calculate the nth Fibonacci number. So we started with representing it as a recurrence relation, where we say like the 0th Fibonacci number is 0, the first Fibonacci number is 1, then any later Fibonacci number is the sum of the previous two. Can you see this?
Then not yet.
Uh,
So I have to download the details slide.
That's actually true. Oh, yeah. I mean,
Also, yeah, something to think about in the meantime is what the time complexity of would be for our current implementation, given the call tree we looked at before.
Recording in progress.
Thank you.
So yeah, are you able to see this okay?
Fibonacci sequence.
Yeah. Yeah, so we're running a program to calculate like the nth Fibonacci number, where it's the index of the sequence where the first two numbers are 0 and 1, then all later numbers are the sum of the previous two. Right, does this look good?
Yeah. I don't have an idea.
Of Fibonacci?
I'm completely.
Yeah.
Computer science, but
Okay, so I guess the Fibonacci sequence is this sequence here. It's a sequence of numbers where we start out and are given the first two numbers, 0 and 1. Then you can calculate any number later on in the sequence by adding up the previous two. So for example, after 0 and 1, the next number is 1, since that's the sum of 0 and 1. The next number is 2, because that's the sum of 1 and 1. Right? Mm-hmm. Yeah, and then we can represent this mathematically using a recurrence relation. And then, for example, this says explicitly that the 0th and first Fibonacci numbers are 0 and 1. And then via the recurrence at the bottom, we know that like the second Fibonacci number is like 2 would be n here. This Fibonacci number is f of 1 plus f of 0, right?
Yeah. Got it.
And then like same thing for the third Fibonacci number. And then we can translate this into a recursive function that takes an integer input. And if it's less than or equal to 1, then we return the same input. And this really means if we put 0 into the function, then we'll return 0. And if we put 1, then we'll return 1.
Okay.
And then otherwise, we then assume that the function is correct. And then for other cases, we return the previous Fibonacci number, like Fibonacci of n minus 1. Fibonacci of n minus 1. This is the previous, and this is the previous Fibonacci number, right? And then we add those together to get the current Fibonacci number.
Got it.
So for example, if we're calculating the fourth Fibonacci number, let's start with the full tree. If we start by calculating the fourth Fibonacci number, it'll first do this check. It'll find that n is not less than or equal to 1. So then it will return the sum of these two, which means we'll first have to calculate Fibonacci 3 and Fibonacci 2. So these are 2 more calls to the same function. And then Fibonacci 3 will have to calculate 2 and 1. And then each 2 will have to calculate 1 and 0. So then, are you familiar with the concept of like time complexity for a program?
Like there's they work on my but
Yeah, I'm interested. You can continue. As long as I'm listening, I'm gonna go.
Okay.
But if you give me like briefly the what is the time?
It's like a function that shows you like generally how long the runtime of a program is scales relative to the input. So if something is linear time complexity, we'd say it's like O of n, which means like if the input doubles, then it takes twice as long to run the program. If something
You want to show response?
like it's like a way, it's just a way to classify how fast your code is. So I guess maybe this could help as an example, but like for example, one way to estimate the time complexity of this code is to estimate it as 2 to the n, where n is our input. Because basically each node here means we're having to do some computation. And this tree is n nodes high, and it doubles in width at each level. So that means like this level is 1, this level is 2, this level is 4, and then this level isn't actually 8, but we'll just simplify it and say it's within 8. So then there are a total of about 2 to the n total units of computation that we have to do. And then it turns out for Fibonacci, in most cases, this is more of like in terms of competitive programming, this is more of like a trivia fact rather than something that's useful. The Fibonacci, this function is actually O of the golden ratio to the n, which is just a tighter bound. You can prove with properties that are specific to the Fibonacci sequence. But either way, the time complexity for this function is exponential, meaning like if we add a constant, if you add a constant amount to n, then the total amount of work we have to do is multiplied by some factor. So the problem with this is that in general, exponential programs are about as bad as things can get. Just calculating the 100th Fibonacci number using this simple program would take about 30,000 years to compute. P is,
30,000 years.
yeah, P is the number of computations are on the scale of like 2 to the 100. So then if we look at the calls we made to fib, can we see any problems or like any areas where we know we're not calculating things optimally?
What was the question?
If we look at the call graph of fib, which is the tree to the left, is there anything we can observe about it that shows us that we're not computing the Fibonacci sequence optimally? Yeah, exactly. So we look and we see that the entire like subtree under fib of 2 is duplicated. And really, we shouldn't be having to do this work twice. Ideally, we only compute fib of 2 once, and then we don't redo the computation. We just use the same value we computed before. So that's actually exactly the optimization that we need to do to improve the time complexity. Every time one of these functions returns, say we return from fib of 2 when we're calculating fib of 3, we'll store somewhere that the output for an input of 2 is, in this case, it's 1, but we'll store the answer. So then when we call Fibonacci of 2 again, we won't call the subtree, and then we'll just look up that the answer is 1, and that will save some work. So the way we do this is, since we have integer inputs, we can use a vector for this, where basically first we look up to see if the index of the input has not had a value set, and we're indicating that using the dummy value -1. And if it's not set, that means we actually have to calculate it, right? And if it is set, then we can just return, then this doesn't execute, and we just look up directly into the array.
What does -1 mean?
-1 is like a placeholder value to say that this hasn't been calculated yet. So for example, at the beginning, like calculated, I guess like if you're not familiar with vectors, you can kind of think of the square bracket notation as like a subscript, and it's just a very long sequence. So at the beginning, like calculated of 2 will be -1 to indicate that we haven't calculated yet. But once like Fibonacci of 2 returns, then here we're going to set this to its actual value, which is 1.
So it's like a basket somewhere when you calculate number.
Yeah, it's essentially just like a sequence. Yeah, so like then the second time when we call Fibonacci of 2, we'll find that calculated of 2 is not -1, so we don't have to do this computation, and we'll just return 1. And then if we look at the call tree, we'll see that we do in fact prune off our repeated work. So to the left is our original code, and to the right is the new code. And we'll see, like say when we calculate Fibonacci 3 for the first time, we do have its entire subtree, but the second time it can just return immediately because we have saved the value and calculated, so we don't do the subcalls anymore.
So why do we do if you have this is 2 times? Why do we do this 2 times?
Yeah, so I guess like there is still each Fibonacci number is still like each input is still in the graph in the tree multiple times, right? But it's only the first time that we have to do more work below it to calculate what the previous Fibonacci numbers are. The second time we calculate the Fibonacci number for any input. So like the second time for 2 or the second time for 3. then we notice that it has no children, so it's no extra work. And then, I guess, are there any ideas for what the time complexity of this solution would be?
1,000 years?
It's luckily a lot faster.
And we can. Like lower 1,000?
So I guess when we're talking about time complexity, we're not talking about the specific amount of time that a program takes to run, but like the function from the input size to how long it takes to run.
Like the one that you said that the linear is like O1.
Yeah, linear is like O of n. It's like a linear function, right? Like, yeah, a quadratic time complexity would be O of n squared.
And you said this one is like exponential.
So the one on the left is exponential.
Maybe it's a lot.
I guess the one on the left is exponential, but then it actually turns out that the one on the right is linear, and that's because we're not doing extra work. Basically, the first time I guess, okay, so there are n total Fibonacci numbers from 0 to n, which are the relevant Fibonacci numbers, and each of those Fibonacci numbers, we're only going to have to essentially do a constant amount of work, which is either look something up or look up the numbers of the children. So if we continue this call graph, it would actually expand like upward like this for computing a higher Fibonacci number. And like you can see, it's like a very long linear shape where it's,
So it's going to be the O and the.
yes, this would be O of n. Yeah, so adding this calculated vector this is dynamic programming, where like all we're adding to the original code is that we're remembering the answers to subproblems, where subproblems are, in this case, the smaller Fibonacci numbers, right? So it's literally the same problem with a smaller input. And then we consider this top-down dynamic programming, because we start with the final thing we want to compute, and then break down the problem into easier and easier ones. For example, 2, 4, 3, then 2, then 1, and bubble up the answer back to the original problem. So there actually is another way to approach this problem, and it actually turns out to, at least in my opinion, I think it's more intuitive and lines up more closely with how we'd actually compute the Fibonacci sequence if someone like hands you a pencil and paper and you have to write it out. So the other approach is called tabulation, and so we're going to work from smaller problems and build up to the final answer we want. So this table just represents all of the Fibonacci numbers that we know so far, and then we're going to build up until we get the desired Fibonacci number. So here we start just knowing the base cases, right? And then we know that the next Fibonacci number is the sum of the previous two. And then we repeat this process, so on and so forth, where we keep adding we keep adding the last two elements to form the next element in this array. Then we can continue that until we get the Fibonacci number we want. And the way this would work in code is we start out, we actually don't even have to initialize this array to anything other than setting the first two values. So then at the start, only these will be filled in. Then we loop over the indices from 2 to the desired Fibonacci number, which is these, and then fill them in. And then each iteration, we set one of these to the sum of the previous two numbers. So after the first iteration, we'd fill in Fibonacci 2. After the second, we'd fill in Fibonacci 3, and so on and so forth. And then, so this is also, and I think more clearly, O of n, as you see, the only complex amount of work we do is in the for loop, which runs n times, does a constant amount of work each time in the for loop. And then there actually is a way to make this even more efficient, although it would have the same time complexity. And it is based on the realization that we only ever need to remember the past two Fibonacci numbers. So for example, if I say that these indices are probably wrong. But let's say I say like the 8th and 9th Fibonacci numbers are 34 and 55. And that's all you need to know, that the next Fibonacci number is 89, because you just add them together. You don't need to know all of the Fibonacci numbers that preceded it. You just need to know the last two, right? So what we can do is we can start out by keeping track of the original last two, calculate the next number, and then every time we calculate a new number, we can just kind of throw away the previous number and then calculate the next number, so on. Like in the same fashion, right? We're only ever keeping track of the next two. And then this will also work to get a solution. So here, I guess we're not really throwing things away. We're just overwriting the same variables again and again. So we start off by saying like the nth Fibonacci number and the n+1th Fibonacci number are the two numbers we'll keep track of. So these start out being the 0th and the first Fibonacci numbers. And then basically like the loop invariant, or whatever is true in the loop, is that nth is the Fibonacci number with index however many times we ran the loop, which means basically each time we run the loop, we want to advance what nth and n+1 keep track of. So at first, when the loop hasn't run at all, this is nth and this is n+1, right? Then we run it again, and then we want this to be nth and this to be n+1, right? And then we'll keep advancing it until we run it 5 times, and nth is the 5th Fibonacci number, and that's what we return. So more specifically, what's happening like on the interior of the loop, let's say nth is the first Fibonacci number 1, n+1 is the second Fibonacci number, also 1. First, we'll calculate what n+2 is, which is the sum of the previous two. And then we set our new nth to the previous n+1 and the new n+1 to the previous n+2. And then this is all we need to do. It will continue as follows, where they compute the next one and then just essentially relabel them. So we're keeping our loop invariant true. That nth is the Fibonacci number with index however many times we ran the loop. We run the loop n times, and nth will be the Fibonacci number with index big N. So as a recap to this approach, tabulation is a bottom-up form of GP, where we start from small subproblems and work on to larger ones. Here we actually started from our base case instead of waiting for like the recursion call tree to work down there, and use that to build up until we reached our original question. And this brings us to a better general notion of what dynamic programming is, which is, just like we said in the beginning, breaking down a problem into subproblems to solve it more easily, whether or not you start with the smallest subproblems and work your way up, or break down from the largest problem into smaller and smaller subproblems, right? We can do it recursively, either with memoization, which is just remembering the answer for previous inputs, or iteratively working bottom up to get to our solution. And then really, this means that the key components you need to solve any dynamic programming are just to define what the base case are, define what the smallest problems that you want to solve are, or that are usually trivial to solve. So for the Fibonacci sequence, the base case would just be the first two numbers. And we also want to know the transition, which is how we get from a smaller subproblem to a slightly larger subproblem. So for the Fibonacci sequence, it is just the transition is literally baked into the recurrence relation. And this means that actually if you can code a recursive solution, usually basically all the way there, because coding like the recursive solution that we originally had forced us to already know what the base case is and what the transition is. Right, so lots of times you can code a recursive solution, then add a data structure to keep track of your previous results. See, so another problem we can apply this to is trying to figure out how many ways we can fill a 2x(n) rectangle with 2x1 dominoes. So, like as an example, there are 2 ways to fill a 2x2 rectangle with 2x1 dominoes. You can either fill them with 2 vertical dominoes or 2 horizontal dominoes. Right. So I think a good way to start with this problem is try to work with a concrete example, which is, let's say we want to fill a 2x5 rectangle with 2x1 dominoes, and we want to count the ways to do that. So I guess we could like start doing this haphazardly, or let's say we like place a domino here, place a domino here, and like fill this out until you realize that like this actually won't work. We want to fill the grid. And then maybe with some experimentation, we'll eventually realize that in order to fill the rectangle, we'll always have to like, it seems kind of obvious, but we'll always have to have like a square here and here to like have a flat edge on the right. And then the only way to have a flat edge on the right is either to have like one domino upright like this, or to have 2 dominoes on the side, right? It's like maybe it's like pretty obvious, but it's like you basically don't want to ever want to like stagger your 2 dominoes on the right like this, right? And then you notice, so no matter what you do, whether you use 2 dominoes on the side or 1 domino on the vertically, then we break it, then we get the exact same problem with the small input. So if we end it with 2 dominoes going horizontally, then the number of ways to fill this 2x5 rectangle that end in 2 dominoes horizontally is the same as the number of ways to fill this 2x3 rectangle. And then the number of ways to fill a 2x5 rectangle with the left or with the right edge being filled by a vertical domino is the number of ways to fill this 2x4 rectangle. And then that gives us our transition for how we compute larger problems based off of smaller ones. And then say if we wanted to go bottom up in the other direction, we consider, okay, let's say for an empty grid, it's kind of weird to think about there, but there's exactly one way to fill it, which is just to use no dominoes. And then there's one way to fill a single width grid, which is just with 1 domino. And there are 2 ways to fill the 2x2 grid, like we discussed before. But then we notice that these 2 ways either come from building off the case with the 0 domino by adding 2 horizontal ones, or building off the case with the 1 domino by adding 1 vertical one. So we're adding up the number of ways to fill the grid that's 1 smaller with dominoes, plus the number of ways to fill the grid that's 2 smaller with dominoes. And then, as we discussed, these are like the base cases. Then since the rightmost dominoes must be either horizontal or vertical, we add up the number of ways to fill it such that the rightmost are horizontal, plus the number of ways to fill the grid such that the rightmost is vertical. And then that gives a recurrence relation that looks like this. And then when we translate this into code, we see it's the same recurrence as the Fibonacci sequence actually, where each number is the same as the sum of the previous 2. We just have different numbers for the base cases. And then the code here is the bottom-up tabulation solution, where we start out by filling a vector with 1s, just because that's easier computationally, and then set each element to the sum of the previous 2. So like this becomes 2, this becomes 3. See, does this look good? Okay. So next we solved the Fibonacci number problem twice, but there are a much wider range of problems that DP can use to apply. So this one's going to be a pretty different one. And in this, we want to consider how many number of unique paths there are, basically from the top right or from the top left of a grid to the bottom right of a grid, where we can only move down or right at each step. So for example, like this could be one unique path, another unique path would be the same, except we like take this turn earlier, or this could be a path, or this could be a path, or like this is a path, and there are a bunch, as you can see. So the first step we want to do is wanting to try to figure out the key things we discussed before, which is trying to formalize it and write out the base case and the recurrence. So the easiest thing to know is that no matter what the grid looks like, there's exactly one path to the start location, which is just like the empty sequence of moves. And then we observe that the row out from there must either, to get to any particular spot, it must have either moved down or moved right. And those are the only two ways we can reach any particular spot. Kind of like the only two ways we can reach any particular grid of dominoes is either to come from like two horizontal dominoes or come from one vertical domino. So it's like we're just defining the transition between subproblems. So if we actually look at how this algorithm gets implemented, we'll start by knowing that there's only one unique path to the start. And then we consider what information we can gain and in what order to figure things out. So for example, if we look at this square, can we tell how many ways there are to reach this from what we have on the board so far? Yeah, one, right? Since our only way to come to it is to move right from the start. And then we can repeat this logic, right? There's only one way to reach this square, because you must have also came left. There's nowhere to come down from, right? Can't move up. And that means there's only one way to reach all of these squares as well. And then following this logic, the next like low-hanging fruit is to say there's only one way to reach anything in the initial vertical column, just because you just have to have moved straight down from the start in order to reach there. Then I guess things get more interesting when we get to like the main part of our problem, when we consider this square, and then we know that we either must have came down or came left to get here, which means we either came from the one way of the square above or the one way of the square to the left to get to, right? There are two paths to that square we just filled in. Here, we'll add in the number of ways to get to the above square or to the left square again to get 3. And we continue this pattern like this. Same thing for here until we fill out how many ways there are to get to the finish. We can write this out explicitly. We say the transition, where W sub ij is the number of ways to get to a certain row, column, coordinate, is the number of ways to get to the one in the previous row, plus the number of ways to get to the one in the previous column. And then when we translate this into code, this is another bottom-up solution. We start out by filling the grid with zeros. We fill in the top row and the left column with 1s. And then for every remaining cell, we add up the number of ways to get to the above cell and the number of ways to get to the left cell. And it's one thing we have to be slightly careful about is the order we traverse this in, because this is all zeros. We don't want to like start out by adding the number of ways to finish immediately, because the cells it depends on aren't ready yet. The only cells that are like that we've finished computing are the top row and the left column, right? So we have to go basically left to right, top to bottom, in order to compute things in the right order. Okay, here is another problem. Coin change, it's a pretty well-known problem. And it's the case where we're given an array of coins, representing coins of different denominations, and some number amount, which is the amount we want to add our coins up to. We want to figure out the fewest number of coins we need to make up that amount, where we can use as many coins of any denomination that we want to. So for example, in the first example, we have coins of denominations 1, 2, and 5, and we want to basically figure out the minimum number of coins we need to create some collection of coins with value 11. So here the minimum number of coins is 3, just to use a 5 coin, and a 1 coin. For the second example, we only have 2 value coins, and we want to build up to the value 3, and we cannot do that, so we return -1. We can only ever add up to even numbers. And then in the last example, we see that if we want to build up to an amount of 0, then we just choose 0 coins. So now, rather than starting by thinking about the base case, we'll start by thinking about like what's the transition we need to do to figure out this problem. This kind of thinking is kind of similar to like doing a proof by induction, like if you use that for like discrete math, where you assume you have some way to solve the problem, you assume that you solve the problem on smaller inputs, and you show that if you can solve the problem on smaller inputs, then you can solve it on a larger input. So for example, let's say for all smaller inputs, that is for all values less than our true target value, we know the minimum number of coins we need to get there, right? Like if our coins are 2, 5, and 8, we know that we can't get 3, right? But we can make 5 out of 1 5 coin, right? So now let's say we need to figure out how many coins we need to add up to a value of 7. Does anyone have ideas of how we use our previous computation to get this?
So we have to use 5 and 8 to get 9.
Mm-hmm.
And we can add up that to whatever.
You can only add. So for example, we start off at 0. We got to 2 by adding 2, right? We got to 4 by adding another 2. We could get from 0 to 5 by adding 5. And we could get from 4 to 6 by adding 2. I want to see, I guess, like first want to feel like, can we get to 7? Then if we can, what's the minimum number of additions we need in order to get to 7? If we want to solve the subproblem, we want to find the minimum number of coins needed to reach the value 7.
5 and 2.
Yeah. And then as we notice that we get there specifically by like essentially coming from 5 or coming from 2, which are the 2 values we've already computed, right? And more generally, we must come from one of these 3 denominations of coins. So we can look at for each coin, where would we have come from if that's like the last coin we're adding in order to reach 7, and then how many coins do we need in that last step? And we need 1 more coin beyond that to go from the last step from here. So for example, for 7, we'd say we either, if we're like adding coins to a pile sequentially and we build up to 7, we say we either, just because we have a limited set of coins, we either added a 2, 5, or 8. Doesn't make sense that we've added an 8 because you can't come from a negative number of coins. And then you could have come from a 2 if you added a 5 coin. Or you could have added you could have come from 5 if you added a 2 coin, right? And then that basically means, then we look at the number of coins needed for the previous steps and see that the minimum number of coins you need to get to a previous step is 1, which means that the minimum number of coins to get to the current step is 1 more than that, since you need to add 1 more coin. So this becomes 2, or it's like 1 plus the minimum of these 2, right? So then, actually, I guess we could continue this. So for 8, we know that we either last used a 2 coin, a 5 coin, or an 8 coin, right? We could have used a 2 coin to come from 6, 5 from 3, except we really couldn't have since it's a -1, or used an 8 to come from 0. And then the numbers we're comparing, we're really not comparing this edge, but we could have used this 8 coin to come from 0, which would have been 1 coins total, like 1 plus the 0, or we could have used a 2 coin to come from the 6, which could have been 4 coins total, right? Add 1 to this 3, and then we find the minimum of these values to know the minimum number of ways to get to 8, which is 1, right? And then let's say we want to find the minimum number of coins we need to get to 9. Again, we consider all possible previous values, which is -8, 5, or 1, which is 1 or 4, or -8, 5, or 2, which is 1 or 4 or 7. And then the minimum of the previous valid values are 2, so we add 1 to that to know that it must have taken 3 coins to get to 9. And we see this kind of lines up with what we think. We could either come from 7, which means we just used a 2 coin, then we know that 7 came from like a 5 and a 2, or a 2 and a 5, or 9 came from 4, which means we could have used like a 2, then 2, then a 5. Like the specific combinations we choose doesn't matter, but we're keeping track of like just the right amount of information we need to know the minimum number of coins. So if we think about our transition and base case,
I have a question. The 7 must 3 the number of points. 2. And if I go to 9, so from 7, I add 2, I go to 9. So it's going to be 2 plus 1 is 3,
yeah,
because 2 is 1.
because like I guess we're adding 1 piece to 2 coin. It has value 2, but it counts as 1 coin. So we're like counting the number of coins. Is that your question?
Yeah. Good question. Sorry.
No, you're good.
Thank you.
Yeah. Yeah, so if we want to solve this more generally, are there any ideas what either our transition would be or what our base case would be?
Are you talking about the linear part that we talked with the Fibonacci?
It's kind of like how with the Fibonacci sequence, our base case was that the first Fibonacci numbers were 0 and 1. And then our transition was that any Fibonacci number was the sum of the previous 2. So for coin change, it turns out that the only base case we need is that there's one way to reach a value of 0, just to use no coins. And then our transition is, like, remember when we were looking at, say 7, our transition is to check all possible previous values, right? So, which is 2 before, or 5 before, or 8 before. Check the number of coins needed to reach all previous values. Find, and if there are any, find the minimum of them, then add 1. So it's like the min of these 3. And add 1 to get the next value. And that's a transition for how I use previous values to get the next one. And it's like obviously more complicated than Fibonacci number, because it requires more computation. We have to like look at multiple values, and it's also dependent on our particular input, the coins we have to use. But it does give us a way to say if we've solved all smaller problems, which are these, then we have a way to reach the next subproblem. So I guess, does that make sense? I guess we could write this out more formally by saying like let like CTR be a notation, like CTR of A be like the minimum number of coins to reach an amount, right? So the coins to reach of 0 would be, oh wait, sorry, the number of coins needed to reach 0 is 0, not 1. My mistake. So the number of coins needed to reach 0 is 0. And then more generally, like let's make some more space. The number of coins to reach like some value I is the minimum of, like, for all j less than I, sorry, the minimum for like all coins say the capital C is our set of coins, the minimum for all coins of like the number of coins needed to reach the previous value, which is I minus C plus 1. This is I guess a bit more to see whether or not we can reach this in general. We'll have to deal with -1 as a special value, but this is our transition, right? Where, yeah, this is C, and then our value is I. So it's not as straightforward with Fibonacci number where we just added the previous two numbers. We need a for loop to like go through all our coins. This is the place we could have come from, but this does give us a formal transition in base case. So then if we translate this into code, we can use like the same CTR notation. We start by writing out our base case, and then we iterate through all possible amounts, adding them on one by one, and basically filling them out in the CTR array. And then for each amount we fill out, we loop through all the coins here and see, we check if we could have come from it and see if the number of ways it would take if we do come from it is better than the current or see if the number of coins we need if we do come from it is better than the current number of coins we think we need to reach this value. So if you're interested to see like exactly how this code works, we can definitely go over it after, but I'll just leave this here to look at later. Okay, that was the last example problem we had for this workshop. Now we're going to go into the contest, and it's worth noting that at the end of this contest, since it's our last week, we're going to be giving out prizes in the form of gift cards to contest participants based on the total number of contest problems they solved throughout this quarter. So a bit of incentive for coming and showing up, right?
So how long is workshop?
Yeah.
Like, this is the last one?
Yeah, so this is the last one, and it was about weekly since the beginning of the quarter.
So you're gonna have another workshop later? I'm trying to UCLA this fall, but I want to all the summer I go to the computer science group. So you don't have any workshop?
Don't have any for the rest of the quarter over the summer. The fall, we will have the very beginning.
But this one is for previous part. This workshop,
This is for the school. But it's over. This is the last.
not for fall, for
Not
summer.
fall. but we will have a new one.
Okay. So I was in the wrong folder.
Yeah, usually,
Yeah.
usually we start with all the stats when most friends come in. They want to learn about the, we assume no required experience, right?
Yeah.
But then at this point of the year, most people have already done the bit of it, so we assume that.
Yeah, it was like mind blowing. But thank you for having me.
Yeah, thank you for
So
coming.
if you're interested, definitely come to our room. That's
Yeah.
year.
Well, thank you. Yeah, that's- thank you.
So here is a contest link, also feedback form.